Yeah, I think it's not that big a deal.
No, I think R works better for me.
Yeah,
In many ways.
I strongly prefer R for lots of reasons, but I mean the thing about Stata is you could do all your data formatting in R, and then if you're learning models in Stata, you could just bring it into Stata to do the models, right? So you could just write out a CSV file. You could do a write.csv and then just read that into Stata and do your work on that file, right? So, or you could just run the models that you'll be learning will actually be quite easy to run in R as well. But anyway, let's talk about uncertainty. All right. What's that? The slides are up on GitHub.
Well, if you do take the class, I'll be in it because I have to take it. So.
Okay. So you were able to find the slides? Okay. Cool. Slides and homework are up. Okay, so uncertainty. So we're going to kind of continue basically directly from where we left off, thinking about probability distributions by extending that logic to thinking about uncertainty. So here we're going to work from, excuse me, a relatively straightforward kind of problem. We're going to look at political polling data to think about how well polling data should inform our expectation of a real event, right? So here we're looking at data on election polls in Florida for the 2008 presidential election. And we have a series of polls, right? Each row in this data frame is a poll. So I'm showing you the first 6, but we have, I believe, about 100 polls in here. And they'll show us effectively 2 variables of interest. One is the percentage of voters who say they're going to vote for Obama, 2, the percentage of voters who say they're going to vote for McCain. And what I've done here is I've visualized the distribution of these poll results for both candidates. The red shows the distribution of McCain's. This is a density plot. So it's similar to a histogram. So each time we have a value at 40, it pushes the curve up a little bit, right? So what can we say about the most common value in the poll for Obama? What was the modal value for Obama? It's going to be the peak of the curve. Yeah, about 47, somewhere in there. For McCain, peak of the curve, it's going to be just slightly below Obama. But we can see that the poll tends to agree more that this is where McCain is going to come in. There's more evidence in the polls because the peak is higher, right? So there's more density at the mode for McCain than there is for Obama. For Obama, looks like we have a little more uncertainty, right? Some polls are showing that he's going to do very well. And in fact, if we were to look at the 50% range, there's more polls showing Obama having 50% support than showing McCain having 50% support, right? But there's also some polls showing Obama having very little support. So we have a lot of uncertainty, meaning that spread, remember we talked about when we have a distribution that spreads out far, we have less certainty about where any one value is going to be observed, right? Because it could be anywhere across this density plot. For McCain, we have a little bit more of a compressed space. So this is kind of the fundamental challenge, is we have all this data about what could happen, but then the question is what will happen, right? How do we make a guess about what will happen based on this? Okay, so let's first kind of start from principles. So to estimate a proportion of voters supporting a candidate, that is to take a survey that is an electoral poll, right? Like who are you going to vote for? We always want to start with a simple random sample. Why do we want to start with a simple random sample? Well, it's the best. Why is it the best? Well, you have to get insights. Why will a simple random sample give us insights when other kinds of samples, say a snowball sample, would not? You know what a snowball sample is? It's when I ask you, hey, are you going to vote? And you say, so he says, yeah, I'm going to vote. And then I say, okay, do you have a few friends? Are they going to vote? And then we ask her friends, are they going to vote? But the problem there is that I'm probably going to be asking all graduate students in a criminology program. And our graduate students in a criminology program, like the rest of the population, no, right? They're different in a lot of ways. They're highly educated, right? Is certainly one feature of that group compared to the rest of the population. They're probably more likely to prefer Democratic candidates than other candidates, as people with higher levels of education tend to prefer Democratic candidates, right? Okay, so that's a bad method, a snowball method. And the reason it's called a snowball is we pick one and then we roll it down the hill and we get more and more and more and more and more and more and more, right? It's not good if we want to make inferences about a population, right? Why is a simple random sample good? What does that do if we take a simple random sample of voters?
Avoid that kind of bias.
It's exactly right. It's an unbiased sample. Because it's random, any feature that exists in the population has equal likelihood of being sampled into our simple random sample. Because every single unit of the population has the same probability of being sampled. So we're not going to start from a simple point and then collect people who might all be similar on some feature, right? To the extent that a feature exists in the population, a simple random sample should have that feature in its sample in the same proportion that it exists in the population, right? So it should be unbiased for both things we can observe and things we can't observe, right? So simple random sample guarantees with a large enough N that our sample is unbiased. So we always want to start with a simple random sample whenever possible. It's usually not possible, but it is the ideal. And it's usually not possible because what do we need to have a simple random sample? What's the practical difficulty?
You cannot get an even number of voters from different groups.
Well, so that would be if we're trying to stratify, right? If we're trying to say you're in this group, you're in this group, and then we're going to draw some from this group, some from this group. That's called a stratified sample, and that can work. But why is it a simple random sample is hard? Because to get one, we need to assign equal weight, equal likelihood of being sampled to every unit of the population, right? And to do that, we need a list of the population such that we can assign equal probability to everyone to be sampled. Those are hard to come by, right? Sometimes we don't even have a good definition of exactly what our population is. Sometimes we do, but sometimes we don't. So then we're going to ask them their preferences. Do you support Obama? Yes or no? Do you support McCain? Yes or no? I guess we're focused really on, is Obama going to win, right? So we're just going to ask about Obama support. Then we're going to compute the proportion of voters in the sample who support Obama. And to do that, we're just going to sum over the x's because it can take on values of 0 or 1. So when we sum over vectors of 0 and 1, what do we get? We get a count of the ones, right? So we're going to get a count of the people who said yes, they support Obama divided by n, which is going to be just simply the proportion of people in that sample who support Obama. We're going to call that x bar, right? The sample mean. We're going to use x bar, our goal. The reason we take a poll is because we actually want to learn about P, the true proportion of voters who support Obama. We don't know that. That's what we want to know. We want to know P, but we don't know it. What we're going to learn is x bar. And now our job as statisticians is to connect x bar to P, is to use x bar to update what we know about P. Okay, so the first thing we want to ask when we have a sample average, we want to know whether our estimate is biased. Now, in this case, because we have a simple random sample, we know it's not, right? But we'll kind of work through the math to show why it's not. So estimation error, we've seen this before, right, is the estimate minus the truth. So it's whatever we compute from the data minus the true value. That's how wrong we are. So if P equals 0.51 and X bar equals 0.48, what's our estimation error? X bar minus P equals minus 0.03, right? We were wrong by negative 0.03. We had a negative estimation error, right? Okay, what's the problem generally with this formula? Say we don't know P. We'll actually never know if our estimate is biased or unbiased if we do not know the population parameter P, right? We can't know that. So let's think about average error when exact error is unobservable. So we don't know our exact error, right? We have no idea how wrong we are from the truth with any one sample. But if we have a simple random sample, the definition of a simple random sample, right, we're going to call this error. The definition of a simple random sample is such that error bar equals 0. The average error will be equal to 0. The average of all the errors, right? We'll have as many guesses that are wrong on the high side as are wrong on the low side. That's what it means to be unbiased. It means the average of all the error terms will be 0. For something to be unbiased, its average error is 0, right? If something's biased in a positive direction, its average error is positive, right? If something's biased in a negative direction, that means it's guessing too high, right? If something's biased in a negative direction, it means its average error is negative, it's guessing too low. But let's kind of think about how we get there, right? So we're going to treat these data, that is voter preferences, as emerging from a Bernoulli distribution with probability P, right? Remember, a Bernoulli distribution is a coin flip, right? So it provides us a 0 or 1 with probability of 1 set to P. So we're going to treat our voter preferences as if they emerge from a Bernoulli distribution with probability P. That is, any individual voter that we sample has probability P of voting for Obama. We don't know what P is yet, right? But that's the model we're going to use, right? We're kind of already, remember we talked about all models are wrong, some are useful. Here, we're putting a statistical model on voter preferences. We're saying voter preferences follow a Bernoulli distribution with probability P. In this case, that's reasonable, right? Because they can either support Obama or not support Obama. Okay, so here's what our Bernoulli can look like. Let's say I give a 55% probability of voting for, of supporting Obama. I'm going to draw from a binomial distribution. Remember, a Bernoulli is a special case of the binomial where n is equal to 1, right? We'll come back to the binomial in a second, but we're going to say size equals 1, and we're going to draw 10 voters from this distribution with probability of 0.55. And for this sample of 10 voters, we get 8 ones and 2 zeros, right? Because each single one had a 55% chance of coming up 1. For this draw of 10, we obtained an X bar of 0.8. So what's our estimation error here? 0.35. We have a positive estimation error, 0.35. Does that mean it's biased? No, because we would need to repeat this experiment many times to obtain an average error, right? A single error being positive doesn't tell us anything about bias, right? We would want, in order to see bias, we would need to repeat the experiment many times to see if the average of the errors was positive. So let's treat the sample mean itself as a random variable. So on this case, what do I mean by that? Let's take this a little slow. We talked briefly about sampling distributions last time. That's where we're going today. So let's come back and look at this again. So here's that code. This time when I run my sample of 10, I get a 0.5. This time I get a 0.6. This time I get a 0.4. And this time I get a 0.3. So let's take these 4 observations of X bar. So we'll say X bar is 0.5, 0.6, 0.4, 0.3. These are the X bars we observed. The average of X bar here was 0.45. And we could then compute an error from this, right? We could call it error is equal to, if I could spell it right, X bar minus 0.55, right? So we get an average error of negative 0.1 from this sample. Now, am I convinced that that's a bias? Why am I not convinced that's a bias? Small sample size, 4, right? I've only got 4 samples here, so I have no kind of confidence with only 4 observations that I have good measurement on an average, right? Usually I'm going to want to see 50 or so before I start to, and even then I might not be fully certain about it. But what we have here are 4 realizations of possible values of X bar, right? X bar has uncertainty. So we have uncertainty in X, that is who's going to vote, what's your voter preference, 0 or 1. We have 55% certainty that it's going to be 1, but on any single draw, right, there's a 45% chance of a 0. So that's our uncertainty there. But we don't know yet how to talk about uncertainty on our average, and our average of 10 voters, right? Here we can see that we've got 4 possible values that range from 0.25 below to 0.15 above, just for these 4, but of course we could keep going, right? We could keep going and compute more and more and more averages to populate a distribution of possible values of X bar with a sample size of 10. That is a sampling distribution. The possible values that we could observe for a statistic, meaning something we're going to compute from the data, like a sample mean, itself has a distribution. It depends on our sample. So the summary statistic we compute from our data itself has a probability distribution. That is called the sampling distribution. The sampling distribution of the statistic. In this case, X bar is our statistic, and it has a range that we could observe it in. When we know the truth, we can compute that range. When we don't know the truth, we can estimate it. Right? Okay, so is that relatively clear that we have this kind of gap? We have multiple possible realizations of X bar. Are we good on that? That X bar could take on lots of different values, could take on 0.5, 0.6, 0.4, 0.3. For a sample size of 10, right, the theoretical range for X bar, they could take on 10 discrete values, right, anywhere from 0 to 1. But how likely is 0 going to be? How likely is it that we'll observe 0 as a sample mean? Incredibly low. How likely is it we'll observe 1? Also incredibly low, higher than 0 because it's a 0.55, but still very low, right? How likely is it we'll observe 0.7? It's not impossible, right? 0.3, obviously not impossible. We did observe it. But the most common values we expect to observe are going to be 0.5 and 0.6, right? But we have a lot of variation in terms of what we could observe. So let's think about this. So we could treat this as X bar as a random variable itself. We treat P as a random variable following a Bernoulli distribution, right? So P is a process with we model it as if it were a coin flip with a 55% chance of Obama preference for any one voter we draw out. But a binomial variable can represent the average. So a binomial variable represents the number of successes from n Bernoulli trials with probability of success P. So we can write out, in this case, remember that if we say X is distributed Bernoulli P, we can say that the sum of X is distributed binomial and that is, we could draw n voters, and the sum of ones will follow a binomial distribution. The sum of our Bernoulli draws. So we could treat a binomial as basically adding together lots of Bernoulli draws. That's all it is. They all have the same probability of success, and we draw it n times. So Bernoulli has one parameter, p. A binomial has two parameters, n and p. So we can represent the average share of Obama supporters as a binomial random variable. Here we're going to write it out kind of funky, but we'll write it out as, so we can write it as sum of x over n, right? Follows this binomial distribution as well, right? Where we could kind of factor in out and return it as a proportion. Or we could write it as x bar times and follows a binomial. In fact, well, so the mean is going to be proportional. It's not going to be exactly equal. That's fine. All right. Yeah, that's right. So this probability distribution means that x bar itself has uncertainty, right? On any one survey I run, I have no guarantee that x bar is going to land in one place. What I have is uncertainty that x bar could land in a range, right? Of the realization of the sample mean from any particular survey I administer could result in a range of possible values for x bar. So let's kind of run this again. So here I'm going to run a 10, kind of repeating what we just did, right? 0.5, 0.7, 0.3. This is 3 more of those sets of 10 voters, right? So those are 3 more realizations of x bar. But let's recall that the law of large numbers tells us that x bar approaches p as n becomes increasingly large, right? So x bar converges to p for a large n. That is, if our n is 10 million, our estimate of the population, our sample mean will always be nearly equal to the population average, right? As x bar approaches the population size, as n approaches the population size. So let's look at this for 5 voters. Here are the realizations that we got when we drew 5 samples of 10 voters and computed the mean, right? We got 2 at 0.4, 2 at 0.6, 1 at 0.7. We're just going to do a histogram of these. So this is 5 samples of 10 voters. This is now 10 samples of 10 voters. So we had 5 observations at 0.6, and I put the dotted line here to indicate the true value of p. We have 3 observations at 0.5, 1 observation at 0.8, 1 observation at 0.4. So already we're seeing between these two that our set of 10 samples of 10 voters is already converging better on 0.55. Let's move up to 100. Now we have 30 samples that had a mean of 0.5. We have 21 or 22 samples with a mean of 0.6. And we can see kind of a spread, right? We only have a handful at 0.2, a handful at 0.8, none at 0, none at 1. Here we are at 1,000. And we can see that the line at 0.6 is slightly, the bar at 0.6 is slightly higher than the bar at 0.5, as we would expect, right? Because the mean is 0.55. But we can see that the distribution itself, right, is kind of coming together and really converging around 0.55 as our n increases, as we draw more samples. So here we have 1,000 samples of 10 voters. And sometimes we observe an extreme value like 0 or 1, but it's very rare. So if you were looking at this plot and you had to guess, if I randomly sample one set of 10 voters, what's the most likely proportion I'm going to observe? What is my best guess for what proportion I might see? It's my best guess for x bar. My best guess is going to be 0.6 or 0.5, right? Because those are the highest bars. When we're looking at these plots, the highest always tells us the most likely. This is the true distribution. So here I'm actually plotting out using a binomial cumulative density function, or probability density function rather, to display the true distribution for a binomial 10.55, and this is what it looks like. And those two distributions look really similar, don't they? So once we're at 1,000 repetitions of the experiment, we've more or less converged to the true distribution. Now you'll see that the x-axis here is 0 to 1 here because I'm computing it as a proportion. Here it's 0 to 10. That's because the binomial naturally gives us a count. But if we divide by n, we convert it to a proportion, right? But these two distributions are virtually identical. So once we're at 1,000 repetitions, again, we're doing a Monte Carlo simulation, right? We're just repeating our binomial draw, that is, draw 10 voters over and over and over and over and over again. We more or less exactly replicate the true binomial probability distribution. That's the law of large numbers, right? Okay. So this is kind of what we know from the math, right? We know this is what the distribution looks like. And we know from theory, with the law of large numbers, that if we repeat an experiment a large number of times, we can approximate the true probability distribution. So that link is going to underlie a lot of what we do next, right? That link between saying that if we repeat this experiment many times, we can obtain the true probability distribution for the sample mean, right? That assumption is going to underlie virtually all of our uncertainty work in statistics, at least from a frequentist standpoint. Okay, so let's treat our estimator, or our statistic we compute from the data, as itself a random variable. We know x bar n approaches e of x, which is equal to mu, which is equal to p in this case, right? We know that that converges as n becomes large. We just saw that. So if we resample x from the same population a large number of times, then compute x bar for each of those samples, the distribution of the sampled values of x bar approximates the true sampling distribution of x bar, right? This is our approximation based on resampling, where we actually physically had our computer compute 1,000 samples of 10. This is the true sampling distribution of x, right? Where this is what, if we just compute the probability density, knowing p, this is what we obtain. So the sampling distribution is this theoretical distribution from which values of x bar are sampled. That is, this is where x bar comes from. We could think of this as the data generating process that gives us x bar. So anytime I draw a sample, my value of x bar is coming from this probability distribution, right? I have a chance of drawing drawing a 3 proportional to the height of this bar. I have a chance of drawing a 5 proportional to the height of this bar. Chance of drawing a 6 proportional to the height of this bar. Right, that is 5 Obama supporters, 6 Obama supporters. A chance of drawing 10 Obama supporters proportional to the height of this bar. That is very low. And actually, in this case, we can just read it off as probability, right? I have about a 25% chance of drawing a 6. I have about a 25% chance of drawing a 5. I have about a 7.5% chance of drawing a 3, 7.5% chance of drawing. You can follow, right? We can read that off the y-axis directly with the probability density. Okay, so the law of large numbers and the convergence of, and hence the convergence of the sample mean to the population mean depends on simple random sampling. Doesn't necessarily depend on simple random sampling. Let me rephrase. It depends on an unbiased sample. We can obtain an unbiased sample in several ways. Simple random sampling is the easiest, the most straightforward way to do it. But this holds under simple random sampling. It does not hold if we have a biased sample. So if we have a biased sample, these methods just don't work. That is, if our estimation error is pushed in one direction or the other. Obviously, if our estimation error is systematically higher, if we draw a large number of samples, what's going to happen to X bar? If our sample is systematically higher than the population average, even if we draw a large number of samples, our X bar is always going to be higher than P, right? The law of large numbers does not help us there because there's a bias in every time we draw X bar out. Okay, so under simple random sampling, right? And again, this is just kind of proving that simple random sampling works, right? Bias is equal to the expectation of X bar. So we could say that bias is equal to the expectation of the estimation error, which is equal to the expectation of the estimate minus the truth, which is equal to the expectation of X bar minus P. That's how we compute sampling error, is the average of the average. When we say E of X bar, we mean the expectation of the sampling average, which is another way of saying the average of the average. If the average of the average minus P is equal to 0, we have an unbiased sample. So we can compute bias as the average of the average minus P, or the expectation of X bar minus P. Under simple random sampling, this is equal to P exactly, right? Because every unit has equal chance of being sampled, so P minus P equals 0. That's just a definition of how a simple random sample works. But this is how we would compute bias in a more formal way. Is the expectation of the sample average minus P, minus the truth. The average of the average minus the truth across a number of repeated samples. So, of course, this doesn't mean that we don't have error for any one realization, right? Bias is systematic, though. Error is an inherent part of statistics. Bias is a systematic problem, meaning that it's a problem of the data generating process itself, right? It's a problem of the way we're conducting the experiment. We expect to observe error, right? Error is a natural part of what we do, and we don't know if we're going to guess too high or too low in any one case, right? We have no idea about that if we don't know the true population parameter. But that's not a problem necessarily. Error is not inherently a problem because we can quantify it, right? What's a problem is systematic bias, meaning our guesses are more likely to be too high or more likely to be too low. That's a structural problem with how we've designed the experiment, right? Or structural problem with how we're drawing our sample. That's something systematic in data collection or in study design that we can't correct away very easily. Okay, so an estimator, where are we at on time? Since it's only, y'all just tell me when you want to break today, because we're good. Okay, so feel free to cut me off when you want to take a break. Okay, it's a lot of math, but we're also going to practice and do some coding. So an estimator is biased when the expectation of X bar is not equal to P, right? That is when we have a divergence between our average of averages and the truth. So when the expectation of X bar, that is the middle of our sampling distribution, the mean of our sampling distribution is not equal to P, that is it's higher or lower than P, we have bias. So bias means, yeah, again, the expectation is systematically different. We can call it positive bias, meaning that the expectation of X bar is greater than P. We call that a positive bias. Our numbers are positively biased. Or negative bias means the expectation of X bar is less than P. Typically in statistics, it depends on the question, but we tend to err on a conservative approach in statistics. That is, I typically prefer to err on the side of a negative bias to a positive bias. I typically prefer to understate the problem rather than overstate the problem. But sometimes a negative bias could be overstated, right? So you need to think about your question, right? But we typically err when we're thinking about design and we're thinking about potential sources of bias. We want to get as close as we can to unbiased measures as possible. But that said, we tend to prefer conservative approaches that minimize bias rather than liberal approaches that ignore possibilities of bias. Right, so if you have potential sources of bias in your data, the best approach is typically to be conservative and assume they exist and to do what you can to work around. Okay, so an estimator is consistent. We call an estimator consistent if it converges toward the parameters it increases. So we call an estimator unbiased when the expectation of X bar equals P. We call an estimator consistent when as N increases, it converges to the truth. Right, so unbiased means it is equal to the truth on average, right? And consistent means it approaches the truth, it follows the law of large numbers. When we say something is consistent, it means it follows the law of large numbers. Okay, so in practice, again, we can just work with simple random samples as an ideal, right? In experimental settings, random assignment deals with this well, at least for internal validity, right? In experimental settings, if we randomly assign people to treatment and control, we've ensured that we have equal distribution of the characteristics of the sample distributed across the control and the treatment groups, right? It's a simple random sample there. We have the population list, and then we randomly assign people. Now, when I say that it works for internal validity, right, that means that we can determine the treatment effect within that group, within our sample, quite well. What about external validity? External validity means, can I generalize the findings of my experiment to a larger population? What are the conditions under which I could have external validity in an experiment? I would need 2 layers of randomization for that. I would need my study participants to be drawn from a simple random sample. And then I would need to randomly assign treatment. Only under those conditions can I generalize to the population. Most experiments do not conduct simple random samples from the population. So experiments are typically weak on external validity because they very rarely randomly select people into the experiment. And without that, we have no assurance that the group in the study is comparable to the population, right? Most of the time, it's driven by volunteers. And volunteers for studies are almost certainly different from other groups of people. This is a major problem for lots of different kinds of experimental research. Psychology is notorious for this, but it's not just psychology. I don't know if y'all are familiar with Mechanical Turk. It's this software people are using, designed by Amazon. It has basically people who are paid to take surveys. And so there's a lot of experiments in criminology and in sociology and in social psychology where people are relying on these people online who are paid to take surveys to take these surveys. But there's very clear evidence that this group of people is very different from the general population. And so there's a lot of inferences that are being drawn about the general population based on this group of people who are choosing to take online surveys for pay, right? The contrast in psychology, and why I like to brag on psychology is, I don't know, have either of you taken psychology undergraduate courses? You did, were you forced to do lab experiments?
Yeah, I need to do.
Yeah, so that's almost always a requirement, is if you take an undergraduate psychology class as part of your course credit, you have to take psych lab experiments. Then you become the study population. So the study population for most psychology experiments is undergraduates enrolled at the principal investigators university, right? And it's almost certain that undergraduates at good universities where there are psychology experiments going on are not the same as the general population, right? So we need to think carefully about how far we extend the findings of experiments based on questions of external validity. And I think this is, I'm editorializing a bit here, but this is, I think, a major issue for science in general, because there is this kind of prioritization of evidence from randomized control trials as being better than other kinds of evidence because it has internal validity and it can claim to have identified the causal effect. But in general, all it can claim to have identified is the causal effect for that sample. It does not necessarily mean that they've identified the causal effect for the population, right? And we have to be really careful in how we interpret the differences between the sample average treatment effect and the population average treatment effect. That's my critique of econometrics for the day. Okay, so we can get the population average treatment effect if we combine the two methods of randomization, but we won't go there. So let's move on to computing a measure that we will call the variance. How wrong are we on average? How wrong is our estimate of X bar for any one case on average? How far off is any one guess of X bar likely to be from the mean of X bar, from P, right? So if I were to just draw one sample of 10 voters, what's my average error going to be, right? So we draw a sample. Let's say we go back to I guess we already wrote code out for this, so let's just go back to our code for a moment. Our average error term before, right, when we computed error as X bar was these 4 realizations of what we could have observed for the sample average, and error was X bar minus 0.55. So then we got 4 realizations of error, 0.05, 0.05, 0.15, 0.25. How wrong were we on average? We were minus 0.1 on average off. That was our average error, but we have positive and negative errors here, right? That doesn't tell us absolute error. So maybe we want to look at mean error squared to ensure that the sign is always positive. So we get a measure of absolute error. And in this case, our mean error squared was 0.0225. So we could take the square root of that to convert that back into the terms of the data. So on average, we were wrong by 0.15 here. That's our standard deviation. We were wrong by an average of 0.15. For those guesses. Now, to compute this in general, for a binomial distribution, we have a definition of the variance. The definition of the variance for a binomial is P times 1 minus P. That is the probability of success times the probability of failure divided by n. That's the variance. To obtain the standard deviation, we simply take the square root of P times 1 minus P over n. So in this case, effectively what that numerator is doing is it's telling us how much wiggle is there, right? So P times 1 minus P, when is that at its maximum? What is P times 1 minus P when P equals 0.5? Equals 0.5 times 0.5 equals 0.25, right? What about when P equals 0.9? Then we get 0.9 times 1 minus 0.9. We're going to get 0.9 times 0.1 is equal to 0.09, right? So the variance is lower when P is higher. Variance on a binomial is maximized when P is 0.5. And that makes sense, right? If you have a 50-50 chance, then you have more uncertainty. You're going to observe, you have less certainty that it's going to be a success. If you have a 40% chance of success, you're going to guess 0 every time, right? Because it's, if you were placing a bet, right? If you're saying, bet $1, is it going to be 0 or 1? And I'm telling you there's a 40% chance it's going to be a 1. A smart person will bet 0 every single time because they'll win 60% of the time, right? There's less variance. There's more certainty when P moves away from 0.5. So in this case, we estimate a variance of 0.025. We can take the square root of that to get a standard deviation of 0.16. And again, this is scaled by n, right? So there we were just computing p times 1 minus p, but divide it by the sample size and we'll get an estimate of the standard error, because of course, as our sample size grows, we have more certainty that what will happen. What happens as our sample size grows? We lower the variance because of the law of large numbers, because it's going to converge to the mean as n increases, right? So when we sample 10 voters, our estimate of the share of the population that supports Obama should have an average absolute error of about 0.16. Our guess should be wrong by about 16 points for a 10 voter sample on average, right? That's pretty noisy, given that we want to, given that we expect this to be a close election. We don't expect Obama to win 90-10. So if we expected Obama's margin, if we expected a candidate to have 90% of the vote, an error of 0.16, we may not care, right? Because we're interested in, does that candidate get above 50%? And if we expect them to get 90% and we expect to be wrong by 15%, then on average, it's very rare that we're going to guess below 50% for that candidate with an error of 0.16, right? With an average error of 0.16. We'll see more about that as we go. Here's the impact of n on our standard error. We could see, right, that it's a function of, the standard error is a function of 1 over the square root of n. So this is the variance, right, sigma squared. If we take the square root of this, right, the square root here is going to put a square root of n in the denominator. And so the standard error is the standard deviation. Sorry, I didn't define that. A standard error is a special term that we use to define the standard deviation of a sampling distribution of a parameter, right? So the sampling distribution of some statistic of interest is called a standard error. And standard deviations and standard errors are a function of n. They're an inverse quadratic, right? Or an inverse square root, rather. So we can see a really clear curvilinear relationship between n and the estimated size of the standard error. So for our binomial n 0.55, the standard error depends very closely on n. When n is low, when n is 10, we have a relatively high standard error. When n is large, say 50, we have a quite low standard error. When n is 100, our standard error approaches 0. So we don't necessarily need a huge sample size here to obtain a small standard error from our estimate, right? To have relative certainty about our estimate, and that's what the standard error tells us, we don't actually need a particularly large sample. If you ever hear the term power analysis, this is effectively what that is. Power analysis is a method by which we compute the likely uncertainty in our variance for some hypothetical expected effect size, right? So say we expect P to be 0.55, we could plot out, okay, what is our uncertainty going to look like under that scenario for different sample sizes? And then we can choose our sample size based on how much statistical power we think we need. This is a way to kind of reverse engineer how big of a sample do I need to detect what I think I'm going to detect with some certainty, right? How large of a sample is going to be large enough to detect something meaningful? We're not going to do power analysis, but if you ever hear someone describe it, it's actually not that complex, right? It's basically using the formula of the standard error to reverse engineer n, to solve for n under a particular assumed value of p. Right, we're just solving for n on this equation. It's pretty simple. I think you'll find as you go that most times things that sound really complicated when people say them in statistical terms are actually incredibly simple once you know how to do them, right? That's the kind of, I guess, joy of learning this stuff. Okay, so in general, the standard error of a sample mean x bar n where X is a sample of n IID random variables, right? That is when X emerges from a simple random sample. We can define the standard error of the sample mean as the standard deviation of X divided by the square root of n, where n is the number of samples we're trying. N is our sample size. So the standard error of X bar is equal to the standard deviation of X divided by the square root of n. So that is, we can compute our standard error by taking our observed standard deviation and dividing by the square root of it. So we can move from the standard deviation of an observed variable to the standard error of its sample mean, right? By taking that observed standard deviation, that is taking the variance in the original variable and dividing it by the square root of n. That is, how much variance is there in the data itself is going to be important for determining how much variance there is in the mean, right? So if the data has a ton of variance in it, the mean could be really spread out. But if the data has very little variance in it, then the mean is going to be more compact. And of course, as n increases, we get convergence on X bar, right? And so we expect to see less distribution on X bar. So that's what that square root of n does. It compresses it as n increases. So we use the observed data to approximate the standard deviation of the sampling distribution. And again, this is the standard error of X bar kind of observed. We don't necessarily know the standard error relative to the truth unless we know the truth, right? But tells us how far away X bar is from expectation of X on average. Let's take 5 here. Is that cool? I want to take a breath and have a sip of coffee. And then we'll come back in just a moment. Let's get back to stats. I'm sorry. Okay, so the standard error of the sampling distribution. That's a thing we're going to focus on for the rest of the day. The standard error of the sampling distribution. It's a weird concept, but it's really powerful. Okay, so let's return to our voter polls. So we are going to take that polls data. We're going to subset it to Florida, right? Because here we're really just wanting to predict a single state because that's the question that we're looking at. And we only need the Obama variable, right? That's the only variable that we're interested in. So we're going to subset the data to only Florida polls with the only measure we're interested in is the Obama measure. So each of these, each row here represents a draw from the sampling distribution of voters in Florida, right? Each one is a realization of some potential sample of voters, right? And then we obtain a sample mean of how many of those voters support Obama, right? So each one of these is a sampling distribution where Obama support is P, right? And each of these is a realization of X bar, just as we were doing in our simulation. So here's a histogram of the distribution of those results, right? This is what the distribution of observed Obama support looks like. So we can use the central limit theorem. So, okay. When we add, so each, sorry, we're kind of moving from a Bernoulli to a binomial again. And we add Bernoulli variables together, we actually get convergence to a normal, right? So in this case, we're adding these Bernoullis together and we get a binomial from the Bernoullis. But what if we had a bunch of binomials together, right? So if we add a bunch of binomial random variables together, the distribution of a large number of binomial variables summed together approaches a normal distribution. And this is the central limit theorem, right? The mean of a binomial random variable right? The mean of a distribution of binomial random variables approaches a normal distribution with mean E of X and standard deviation variance of X over N as N approaches infinity. So when we add lots of binomials together, something like this, it will converge to a normal distribution when N is large, if the sample is unbiased. The distribution of these means becomes normal. Not the variable itself, right? But the distribution of the mean of the variable. So the voter variable, right, is still distributed Bernoulli, P, and the distribution of any single realization of vote share is distributed binomial in P. But the distribution of the average vote share for sufficiently large N is distributed normal. And that's powerful. So X bar of N, the sample mean of vote shares for the binomial, follows a normal distribution. So if we resample X many times, we get a normal distribution. So using our polling data, we obtain a distribution of X bar with a mean of 46.1 and a standard error of 3.4. Right? And again, our standard error here, we can just compute this from the data. Right? Let's go to Florida data. On everything. Okay, so here's FL, right? We have 71 observations. The mean of FL is 46.18. So that's the center of our estimated distribution. And the standard deviation, FL, Obama, is 3.36. The standard error is actually going to be the variance of X over, sorry, that's not quite right. We'll come back to that. Sorry, I'm trying to remind myself what N was there. And N should be the number of voters included, but it's fine. We'll come back to that. Here's the observed sample means, right? The blue is our observed sample means. And here's a normal 46.13.4. No. I don't recall how we got the 3.4 standard error. I'm sorry. Oh, it's just the standard deviation of the observed. Okay. Okay, so the standard deviation of the observed there, we estimated at 3.4, and the mean is 46.2. So we're going to use the standard deviation of the observed because we're saying effectively what we're doing with this large set of polls is we're collecting enough data to approximate the sampling distribution, right? And so our approximation results in this empty normal curve. Our observed data is the blue curve. And we can see that the approximation is pretty darn close to the observed, right? That is, when we take the average of a lot of binomials, we take the average of a lot of realizations of a binomial random variable. So here we could think of each of these polls as one possible draw from a binomial. And maybe it'll help if we do, it'll help me anyway. If we divide it by 100 to see these as proportions rather than as percentages. But each of these draws is the proportion of voters who said yes to Obama out of their sample, right? So we can think of each of these as a draw from a binomial distribution. And if we assume that they're drawing from the same binomial distribution, meaning P is the same set of voters that they could sample, And we assume maybe that it's all happening at the same time, right? So that that perhaps, because obviously like during a presidential campaign, support for Obama will change over time because of events in the campaign, right? But let's say it all happens at the exact same time with the exact same list of voters. These are the estimates we draw, right? We can use that then to say that for a sufficiently large N will approximate the sampling distribution of the truth, right? So here's what that looks like. The theoretical sampling distribution and the observed one. So how certain are we about this estimate? To provide an estimate of how certain we are, we can compute what's called a confidence interval. So typically when we compute a confidence interval, first step is to choose a confidence level. The canonical ones are 0.9, 0.95, 0.99. I typically work with a 0.9 confidence interval. I think those are generally the most useful because oftentimes the large tails can be quite unstable unless we have lots of data. But 0.95 is pretty conventional as well. In a Bayesian context, you'll even see sometimes people using a 0.8 because it can be hard to estimate tails. But we'll go with 0.9 or 0.95. Then, because we know that the sampling distribution of the mean theoretically follows a normal for a large N, we could use what we know about the normal distribution to compute a quantile that corresponds to that confidence level. So we can say, if we know what the standard deviation is, well, so let's kind of, then what we can do from there is we can multiply the value of this quantile by the standard error of the quantity and subtract and add it from the mean to obtain a symmetric confidence interval. Now that's a lot. Let's kind of work through this slowly. First, we're going to obtain a 90% confidence interval of Obama vote share in Florida. I guess to clarify, this slide is our algorithm. This is the algorithm for the confidence interval. This is the steps we take to compute the interval, right? Step one, choose our level. Step two, obtain the quantile that corresponds to the level of confidence that we want to obtain, and then multiply that by the standard error, and then add and subtract that from the mean. Okay, so first let's start with a 90% confidence interval for our Obama vote share. So we typically describe this as an alpha value. I'm going to choose a 90% confidence interval. So that corresponds to an alpha of 0.1. 1 minus 0.9 is 0.1. What this does is we want to ask what is a 90% probability range for the vote share. What's the 90% range within which the value of the mean could expect to be observed? Because a normal is symmetric, once we've obtained, we want to kind of slice the probability distribution. So we want to have 10% of the probability distribution excluded. We want to exclude extreme values. And because normal is symmetric, that means we basically want to trim 5% off both sides of the distribution. Right, so we're going to do 0 plus alpha over 2 and 1 minus alpha over 2. That is, we're going to look at the 0.95 and 0.05 quantiles of the normal. We're going to look at the 5th percentile and the 95th percentile for a 90% interval. For a 95% interval, what would we be looking at? 2.5 and 97.5. Yeah. And for a 99, we'd be looking at 0.005 and 99.5. So we can use the Q norm function to obtain on a normal 0, 1, how many standard errors away, how many standard deviations away we would need to be from the mean to contain 95% of the probability mass on either, or 90% of the probability mass on either side of 0.05 and 0.95. So we get minus 1.64 and 0.164. These are z-scores, right? We've seen these before. We were just talking about high school stats. These would be your critical value for your z test. Right? But these are how many standard deviations away from the mean is something that is at the 5th percentile of variance on a normal, right? The 5th percentile of values of the distribution of a normal. We can obtain basically 90% of the mass of a normal distribution by looking between the minus 1.6 and the 1.6 standard deviation of the mean, right? What that looks like in practice is this. This dark blue bar is the 90% interval, right? This light blue bar is the 95% interval, and this lighter blue bar is the 99% interval, right? So we're basically slicing off different chunks of the distribution to obtain different proportions of the probability mass. But we can compute this interval as x bar plus or minus z alpha over 2. So that's plus or minus 1.6. We're rounding, right? But notice that minus 1.6 and 1.6, that's symmetric, right? We know it's always going to be symmetric. So we actually only need to compute that once. We don't need to do it for both 0.05 and 0.95. We can just do it for one of them. We can say x bar plus or minus z, 1.6, times the standard error that we've estimated. So we take the mean of Obama's vote share in Florida from the sample, minus 1.64 times the standard deviation of the vote share, which is equal to the standard error of our estimated sampling distribution, to obtain a lower bound of 40.66. And we add 1.64 times the standard deviation to obtain an upper bound of 51.7. So our confidence interval, 90% confidence interval for Obama's vote share is 40.6 to 51.7, or 40.7 to 51.7. That's our 90% confidence interval. It ranges by 11 points. That's a pretty wide interval, right? Relative to the outcome. So would you say we have a lot of uncertainty here, or we have a lot of information? There's very little uncertainty. Would you characterize this as low or high uncertainty relative to the outcome of interest, which is who's going to win the election? What's that? Yeah, in Florida. Who's going to win the election in Florida? Based on this confidence interval, do you think you have high or low uncertainty? High-ish? I would say high-ish. Yeah. We don't know who's going to win based on this, right? It's a guess. Safe money's probably on McCain because more of the mass is below 50, but we're not very certain about that. There's a lot of the mass that's above 50 where Obama could win, right? So we don't know. That's what we've learned. We don't know what's going to happen. Now I'll talk about the exact interpretation of the confidence interval in a second, because what we did not learn is that there's a 90% chance of the truth falls between 40.6 and 51.7. That's often how people interpret confidence intervals. Often what people say after they compute a confidence interval is, I'm 90% certain that the true value for the population mean falls between 40.7 and 51.7. We did not learn that. What we learned is that if we repeat the computation of this confidence interval many times on different samples of data, 90% of the time, the truth will be in the interval we computed. That's weird, right? We're appealing to the central limit theorem again. We're saying if we repeat the experiment many times, that is, if I go back here and I conduct a new set of polls, a new set of 70 polls, right? And then I estimate the distribution of those, 90% of the time, when I follow this formula, 90% of the time, the true value of Obama's vote share in the population will be included in that interval. I have no guarantee that this interval covers the truth. I have no information on that. I have no idea where the truth is. So I don't know that there's a 90% chance that this value contains the truth. It either does or it doesn't, right? And we don't know that. But what we know is if we repeat this experiment many times, 90% of the time it would contain the truth. And what it does give us a measure of is not necessarily where the truth is, but it gives us a measure of the uncertainty we have around the truth. How broad or narrow is the band, right? Because we can expect if we repeated the experiments, the location may move a little, right? Because there's always going to be error, but the width of it should remain relatively stable, right? So the width of the interval we would expect would remain stable, even if the location of it moved. It's a subtle, weird thing. This applies to significance tests as well when we get there, right? A significance test does not tell us, I'm 95% sure that this is the effect, right? It tells us that if we repeat this many times, 95% of the time, this test would say yes. Right? Okay, so let's do this to 0.95. So relatively clear on how we get this confidence interval. We can use the Q norm function, which you're not really going to need to use that often, but we'll use it just for these kind of few exercises because we know those critical values, right? Or at least you'll learn them, that a 95% confidence interval roughly corresponds to a z-score of 1.95. And a 90% confidence interval roughly corresponds to a z-score of 1.6. 99 roughly corresponds to a z-score of 3. Right, you'll just kind of memorize these values over time. But we can take the Q norm for a 0.05 and a 0.95 at 0, 1. That's going to come out when we run that to about 1.95. I'm sorry, for the 95%. Let's look at what those give us exactly. So the probs on the Q norm here are plus or minus 1.64. And then in order to compute our 90% confidence interval, it's really simple. We take the average of the sample, take our probabilities that we've estimated for the z-scores, right? Take our z-scores, multiply those times the standard deviation. That's our confidence interval. 40.6 to 51.7. That's our 90% interval. Our 95% interval, we can change our quantiles to 0.025 and 0.975 to get the 2.5th percentile, 97.5th percentile, which contains 95% of the data. That's going to give us plus or minus 1.95, 1.96. And then we just take the average, plus or minus 1.96 times the standard deviation to get our 95% confidence interval. So what do we note about, here's our 90% interval, here's our 95% interval. Oops, sorry, need to redefine probs. There's 90, there's 95. What do we see as the differences? 90, 95. Yeah, the 95 is wider, right? That's the trade-off for that extra uncertainty, right? We want to describe a broader range of possible values, right? And so in order to do that, our interval becomes wider. When we get to 99%, it's going to get substantially wider. Right, the jump from 90 to 95 was only about a point. The jump from 95 to 99 is about 2 points. And we can see that in the shape of the normal, right? To go from, say, here to here, we move really far on the x, right? Because there's a curve here for lower values of q, for lower values of z, you don't have to move that far to gain a lot of mass, right? But as the tails get narrower, we have to move farther and farther out to incorporate more of the mass of the distribution. So it's much easier to grow by a small amount when we're close to the center of the normal. But as we get further out, we have to move pretty far out on x. So typically, when we're looking at a 99% interval, those are going to have they're going to be much, much wider. Right? So as we go up in our confidence level, we go up in alpha, or down in alpha rather, in our critical value, the intervals become much wider. That's the trade-off for kind of more inclusive statement of uncertainty, right? Okay, so what does this interval mean? Well, y'all give me a stab at interpreting this.
Sample data set we collected before in this interval.
So our sample mean here, right, has an exact value. Right, the exact value is this. What does that 95% interval tell us? So we know the sample mean is that, and we know, for example, that like not exactly the same thing as 95% of the data falls in this range, right? Because we could actually take that. Let's take the actual 95% interval of the observed data. It's not going to be the same thing, right? Say 0. So this is just the observed data. We get 37.75 and 51. 95% of the observed data falls in that range, right? But this is narrower a little, right? It's different anyway. It's like a little higher on the right side and a little lower on the left, a little higher on the left side, a little higher on the right side. This tells us about the variability of the sample. This tells us how variable is our estimate of the sample mean. What's the sort of range in which we might expect to, how much spread would we expect to see if we were to repeat this experiment? How confident am I that I would observe a similar value for the sample mean if I were to repeat the experiment? What I'm telling you that 95% of the time, if this were the truth, 95% of the values would fall in this range. Assuming that the truth were the mean was our observed sample mean, 46.2, and the standard deviation, the standard error was the observed standard error. So this tells us how much spread is there in our realization of the sample mean if we were to repeat the experiment. Always interpret it as a matter of spread rather than location, right? Doesn't necessarily tell us that there's a 95% chance that it will fall in this range, right? It just gives us a sense of how variable it is. Because again, every time we repeat the experiment, we could conduct a new confidence interval. Let's kind of think about that for a second. Is there a simulation we could do? Indeed, there is. So remember, we're going to use this normal 46.13.4 to approximate what our distribution looks like. Well, I'm not going to mess with that. What we could do though is we could say those are approximations, right? So what if right, this normal 46.13.4, we're estimating from the observed data. What if the true mean was 46.5, right? And what if this shifted a little over here? And what if the true standard error wasn't 3.4, but it was 3.2? It was slightly narrower, right? The values we would observe when we sample from it would wiggle a bit. Right? We have uncertainty about both of these parameters. This is just, we're using the observed data to approximate. We're not sure that this is the truth for the population. We're using the observed data to approximate that. Okay. Questions? This is tricky. So the exact interpretation of a confidence interval is that if we draw another sample from the same population, the sample value will fall within the computed interval 95% of the time. If we base our interval on the true values from the population. It does not mean that the probability that the true value of the population mean falls within the interval. Doesn't mean that we have a 0.95 probability that we contain the truth. Means that if we redraw, we've got roughly a 95% chance that the sampled mean will be included in that interval 95% of the time. But the true interval, right, is centered on P, which we still don't know. If we draw a large number of samples and construct 95% intervals for each of them, those intervals will contain the truth 95% of the time. So if we repeat the experiment 1,000 times, roughly 95% of the intervals we compute will contain the truth. If we do it 1,000,000 times, exactly 95% of those intervals will contain the truth. So it's an expression of what the computation gives us, not our exact numbers, what the process results in, right? Our exact numbers are not especially meaningful. So this is kind of the fuzzy thing about statistics is you'll see this and like someone will report out, well, it's 39.58784, right? That's the exact number I computed. But we don't actually know that this number represents the truth, right? We just know that that's one possible number we could have observed out of a huge range of possible numbers from repetitions. So typically we don't want to be that exact, right? I'll say my confidence interval, 90%, 95% was 39.6 to 52.8. which indicates a high degree of uncertainty in the outcome of the election. That's how I would interpret something like this. Okay. So confidence intervals are tricky in terms of their interpretation, but they're incredibly simple to compute, right? The mean plus or minus the z-score for your critical value times the standard error computed, which is just the standard deviation of the data. Very simple to compute. Very tricky to interpret. But think of them again, not as an exact measure of uncertainty in your estimator, but as an approximation of how much uncertainty there is in the possible range of values you could observe. You could have observed if you repeated this experiment, right? When we're doing statistics, we're always appealing, when we're doing the frequentist school of statistics, we're always appealing to this idea of repeated hypothetical experiments. We're always appealing to this idea of the sampling distribution and the central limit theorem, right? We're appealing to this idea that we could, in theory, repeat the exact same thing we did over and over and over again and obtain a true sampling distribution from which this confidence interval is one confidence interval drawn from the sampling distribution of confidence intervals we could have observed. Right? Everything has a probability distribution when we're thinking in this way, right? So we can always kind of take a step, we can take a step further and think about what if I repeated this? And then what's the distribution of what I could have observed if I repeated this? That's what we're thinking about when we think about uncertainty and a frequentist standpoint in statistics. Okay. So we're going to go back to our class size experiment for a second. We did a homework on this. Remember that we're looking at the reading scores based on assignment to a small or regular size classroom. So we're looking at whether we have an impact of being assigned to a small class size in kindergarten on later test scores, on 4th grade reading and math test scores, and then also on like high school graduation rates, things like that. So we're looking at a very simple intervention and then looking at the long-term effects of that intervention. Here's the densities for our grade 4 reading and our grade 4 reading scores by class type. So here are the range, right, of what we observe for the 4th grade reading tests. The blue curve indicates the small class size. The red curve indicates the regular class size. Eyeballing this, what do you see? It doesn't look different to me either. Similar distributions. This is why data visualization is so critical, right? Is we can look at this and we can say, well, those don't look like they're different distributions to me. It looks like the two groups of students have very similar spreads for reading scores, right? I don't see what we would expect to see under the context of a clear causal effect is what? And what would that look like here if it had a better score? You would push the location of this direction, right? What we would do is we would just move the location of this. Effectively, it would be to shift the center of mass. We might see the same shape, but we could just move, say the center of mass right now is like 730. Maybe we would bump it up 20 points so that the peak came a little later, right? If it was shifted to the right, that would indicate a clear difference between the groups. But we don't see that here. Okay, so let's compute confidence intervals for each group. I'm going to do some tidyverse kind of trickery to make this a bit simpler, because we can actually combine our standard deviation and our mean computations into a pretty simple function. Right, so I'm going to group by class type. I'm going to summarize where the X bar for reading is just equal to the mean of reading for each class type group. Right, so we're going to get the mean for the small class type and the regular class type. We're going to compute the number of students in each group with the n function. We're going to compute the standard deviation with the standard deviation. And then we're going to compute the standard error of the sample mean with the standard deviation divided by the square root of n, divided by the sample size. So we can just do all of the computations we need to compute the confidence interval in one block of code, right? We can get our standard errors and our means and all that. Now we're going to set a 95% confidence interval. So alpha is going to be 0.05. I'm going to use the Q-norm function, 1 minus alpha over 2, 0, 1 on my normal, which is the z distribution. A normal 0, 1 is the z. So that's what we always use. So the normal quantile, 1 minus alpha over 2, 1 minus alpha over 2. In that case, what is alpha is 0.05? What's alpha over 2? If alpha is 0.05, alpha over 2 is 0.025, right? So alpha equals 0.05, alpha over 2 equals 0.025, 1 minus alpha over 2 gives us 0.975, and alpha over 2 gives us 0.025, right? Those are just the thresholds for that 95% interval that we already defined. So you could just write that in instead of doing the alpha over 2 computation, but this way I could set my alpha wherever I want here and compute the confidence interval the same way, right? Because I have it as a variable. Okay, so plus or minus, I'm going to set this as the lower bound for the confidence interval and the upper bound for the confidence interval. And the only difference between these two equations is just the addition and subtraction. Okay, so I get very quickly my confidence interval for the two groups. My estimate for the average grade 4 reading score for the class size, for the regular class size is 720, and for the small class size is 723. So it's a 3-point difference in the mean. My standard error, or my confidence interval is 716 to 723 for the regular class size and 720 to 727 for the small class size. So I have a 7-point spread on both of them. What do we note about this confidence interval? Anything stand out to you? They look kind of like that. They actually overlap with each other, right? We have this area in here, where the intervals contain the same values. That's going to turn out to be really important. When we're evaluating, when we're interested in thinking about whether two things are different from each other, using the language of statistical significance, we can see that the 716 to 723 interval contains similar space to the 720 to 727 interval, right? These values between 720 and 723 are contained in both intervals. So crudely, we're not too certain that the location of these intervals is different, right? That is, our estimation of our uncertainty about the average for the group contains similar values for both, right? We'll see later that this means that we would reject a statistical significance test for differences between groups at the 95% confidence level. If 95% confidence intervals overlap for two groups, we would reject a statistical significance test. We would reject a t-test, or a z-test in this case. What's our confidence interval for the standard, or for the sample average treatment effect, however? So this is the difference in means, right? The difference in means is the sample average treatment effect, I apologize. So how do we compute the sample average treatment effect from this table? It's going back to like week 1. What's that? The sample average treatment effect. So what's the effect? What is the estimated effect of class type size on grade 4 reading in this sample? 723 minus 720, right? It's just the mean. It's X bar for small minus X bar for regular. X bar for treated minus X bar for control. So in this case, it's about 3. It's 3.5. Is our sample average treatment effect. So what we really want to know is not so much the location of the regular and small group. What we want to know is the regular group doing worse than the small class size group? Or is the small class size group doing better than the regular class size group? We want to know how uncertain are we about the treatment effect, not necessarily just about each group's location. In order to take the standard error of the sample average treatment effect, we can follow a rule for the sum of variances, which you don't need to worry too much about because most of the time your regression will do it for you. But here, what we can do to sum two variances together, so we can add the variances, or I'm sorry, to take the sum of square roots, we take the sum of the squares and then take the square root of the sum of squares. So we sum the standard deviation of the reading scores for group 1, squared, sorry, the standard error of the reading scores for group for the small class size, we square that, and we square the standard error for the regular class size, and then we take the square root of that sum, and we get the standard error of the sample average treatment effect. Effectively, we're doing a weighted average of the two standard errors. But it's 2.6. So we have a sample average treatment effect of 3.5. SATE equals 3.5. We could say the SE of SATE equals 2.6. Is that what we said? Okay. So you're going to get to a point where you can see this is, and this is all you need to see to tell me whether or not this is a statistically significant result. Because what do we know about computing that 95% confidence interval? How do we do it? Right, so Z when alpha equals 0.05, Z of 97.5 plus 1.96. Z 2.5 equals minus 1.96. Right? And so to compute the 95% CI, we take 3.5 plus or minus 1.96 times 2.6. That's all we need to compute that 95% confidence interval for the sample average treatment effect. And so what do we get? Well, let's see what we get. I'm not going to do that math in my head. We get minus 1.7 and 8.7. Roughly, because I mean, roughly 2 times 2.6 is going to be 5.2, 5.3, right? So we're going to end up with 3.5 plus or minus 5.3 more or less. So the interval is really wide. And the likely region we have based on this data is minus 1.7 to 8.7. If we repeat the experiment, how certain are you that we would see a positive effect? Don't know. There's a good chance we wouldn't see a positive effect. There's a good chance we would, right? But there's also a non-zero chance that we wouldn't. And the reason we choose our critical value before we do the test is so we don't cherry pick the width of the interval, right? In theory, we're supposed to choose our threshold, our alpha, prior to doing the test so that we don't choose an interval that will exclude 0. But if it includes 0, and if it includes values on either side of 0, then according to this test, we don't have a lot of confidence in the sign of the sample average treatment effect, meaning what direction it goes. Is it a positive or is it a negative? Based on this, if we want to retain 95%, if we want to retain a 95% confidence level, we don't know. The mass contains values on both sides of 0. So we don't have a lot of certainty here about the direction of the effect, nor the magnitude. Why can I make claims about the magnitude of the effect? 8.7, that sounds maybe kind of big, but 8.7 relative to what? Remember that the mean is 720. So 8.7 relative to 720. Let's see what the maximum effect that we estimated here. Is like a 1.2% jump, right? At best, we're estimating a 1.2% jump in test scores. That's small. So I would call that, I would interpret this, just looking only at this confidence interval and what I know to be the mean of the test scores, right? 2 pieces of information. I could say we're uncertain about the direction of this effect, but if there is an effect, it's small. Even if it could be positive, it could be negative, I don't know. But no matter what I do know, it's small. Because if the interval were like negative 500 to positive 500, I don't know if it's negative or positive, but it could be quite large, right? But in this case, I do learn something, right? I learned that we're not sure if it works, but even if it did, it's not a large effect. Those are the kinds of statements we can make after doing these kinds of analyses. It's not that we didn't learn anything. A null effect doesn't mean we didn't learn anything. We would call this a null result, right? Meaning we don't reject the null hypothesis, which we'll get to in a second. I kind of hate that framework, but the idea here is we don't detect an effect. It doesn't mean we didn't learn anything. Okay, so this is the estimated sampling distribution of the sample average treatment effect with a 95% interval, right? This is the theoretical distribution that we imagine if we were to repeat the experiments and if we assume that what we observed here is the truth, right? That's the assumption we're making. Assume that what we observed here is exactly equal to the true measure of the effect of the study, which of course it's not, but we can make that assumption for a second just to get our heads around this. These, if we repeated it, and this was the true observation, 95% of the values fall in that range. right? And so even if we said, this is definitely the truth, we still have a not insignificant chance of observing something less than zero, less than or equal to zero. And if we were to call anything less than like 5 a very small effect, we have a very good chance of observing a very small effect. Right? Even if we call 8 a relatively small effect, our chance of observing something higher than 7.5 is pretty low. Right? And our chance of observing something that's a very high effect size is virtually 0. Right? Once we get up to 10, we have very little probability mass greater than 10. And again, if we were to repeat the experiment, we may not be certain that the location that our sample average treatment effect was estimated precisely. Its location may be off, but the spread, given our large N, is probably going to be similar. The standard error is probably going to be similar, right? And so we might want to move this distribution a little bit this way or this way. But even if we wiggle the distribution this way or this way, it's not going to fundamentally change our interpretation. If we move it a little bit this way, perhaps we will get an interval that does not include 0, but it would still be a small effect, right? So it's kind of important. The advice I like to follow comes, Andrew Gelman has, hey, Snow, kind of laid this out. Yay, right? Let's go sink into depression because this is the next 6 months. Oh, it's not gonna be that bad. It's nice, it's pretty.
Hate weather. Like, people are like, I hate snow, I hate rain, I hate anything that comes out. If it's weather, like even if it's
Precipitation
sunny,
of any sort. Oh,
not
no, just
even-
all of it.
Yeah.
You prefer to live in a cube, a
Yes.
temperature controlled cube.
Yes, that would be amazing.
Okay, okay.
Like a lizard.
A lizard, yeah.
Great. I want that.
You just want a heat rock to sit on all day?
Yes,
aid in your
but no
digestion?
sun.
That's fine.
I
Okay.
like a mild, cloudy, 74.8 degree day.
Have you heard of Oregon?
Yes. Or have.
Okay. So anyway, okay, we're cool with what this represents. These are the possible values of the SATE we could observe under replications, assuming that what we observed was the truth. So this is our uncertainty, making the strong assumption that what we observed is the truth. And we still have a lot of uncertainty, right? With that strong assumption, if we weaken our assumption that what we observed is not the truth, all we're going to do is we're going to add more wiggle on this. We're going to push it out further, right? So if we think that, we observed X bar to be here, but let's say we think that it could actually be that we're saying that the true value for the sample average treatment effect is right here, right? Based on our observation of X bar. But what if we want to put uncertainty on that, right? Then we could actually say, well, maybe the truth could be more like this, right? And then we could push our interval out even further. We could add additional levels of uncertainty onto it. That's sorry, that I'm like my Bayesian sort of bias is showing here, because that's what a Bayesian framework would do, is then we would simulate it from a distribution where we assume we don't know this, but this is one possible realization of it, right? And so then we could actually get a much wider interval that's probably more reflective of the truth. In a Bayesian context, we'll call those credible intervals when they're based on something called the posterior predictive distribution. Again, we could come back around to that, but you may see those in papers. If you see someone say a credible interval versus a confidence interval or a posterior interval, that's a very similar thing, but it's estimated slightly differently using Bayesian methods. But it's capturing the same sort of idea, right? How uncertain are we about this estimator? The reason I like the Bayes approach is we don't have to do the resampling thing. I don't have to say under theoretical resampling. I can make more direct claims. I'm going to stop talking about Bayes. Okay. So we're clear on what the 95% interval here means, right? If this were the truth, this is the range of possible values of X bar. Of course, we don't know if it's the truth. So let's move to hypothesis testing. The hypothesis test follows very naturally from the confidence interval. It's just an application of the idea of the confidence interval to a formal question. Is this greater or less than 0? Right? So we want to know whether assignment to a small class in kindergarten improves reading scores in 4th grade. Is there a causal effect? That's what we want to know. Now, there's a ton that's been written and said about the use of hypothesis tests to make truth claims, which is kind of what we're doing here, right? I'm going to say, if this passes the hypothesis test, then we say, yes, there is an effect. If it does not pass the test, we'll say, we don't know if there's an effect. But that's a truth claim, right? If it passes the test, I'll say, yes, we know there's an effect. That's not actually what I've learned, right? I've learned that under theoretical replications, 95% of the time, we would detect a value that falls in this range, right? So we want to be cautious with interpreting these. And when we see people link a statistical significance test to a claim that something is, quote, real, we should be dubious, right? It's evidence that something is likely to reoccur when we examine it again, but sometimes we may want to examine it again. Okay, so here's the basic framework for the hypothesis test. Sorry, I'm getting like my critical sort of thing on before I introduce the core concepts, but what are you gonna do? Here are 2 hypotheses. The null hypothesis is that kindergarten class assignment has no effect on 4th grade reading scores. H0 we call the null hypothesis. And effectively, the null hypothesis is no difference between groups. There is no difference between the treatment group and the control group. If we are to compute the sample average treatment effect, right, X bar for treated minus X bar for control, H0 says that that's equal to 0, that the sample average treatment effect is equal to 0. That's H0. The null hypothesis is that the sample average treatment effect equals 0. And we can kind of write this out mathematically. I'm kind of writing it out with words there, but you can say H0 SATE equals 0. H1 SATE not equal to 0. Those are our 2 hypotheses. The null is that the treatment effect is 0. Hypothesis 1 is that the treatment effect is not 0. And we just said has an effect here. So that implies it could be negative or positive. We're not constraining it to be positive or negative in this hypothesis. We can do so, right? But here we're not. So we're going to use our sampling distribution of the sample average treatment effect to test this hypothesis. That is, we're going to use this distribution to test it. So we specified our null. Here's our kind of algorithm for the hypothesis test. We're going to choose a test statistic and a level of alpha. So that is, we're going to choose typically a Z, but we could choose a t-test as well if we want to allow the difference between a Z distribution and a student's t distribution is the student's t's tails are a little bit fatter, so they allow for more extreme values, which means that the normal effectively says extreme values are less likely. The student's t says we might see extreme values. So the student's t is a bit more conservative in terms of allowing possible extreme values to come up under resampling. Choose a test statistic level of alpha. 0.05 is the most conventional for a significance test. I will say, if you're writing in criminology, if you choose anything lower than a 0.95, reviewers are going to jump on you. Because they're going to think that the only reason you did that is so that your results would come out significant when they wouldn't otherwise. But I've seen some arguments that we should choose even higher levels. 0.99 is one that people have suggested. In disciplines like physics, typically they'll choose something that's 5 or 6 standard deviations away from the mean. That would be like a 0.99999, right? Depending on how certain we want to be about the results, right? Okay, then we'll derive the sampling distribution of a test statistic under the null hypothesis. So we'll derive this distribution. What is the sampling distribution of our test statistic? using the observed data. We'll derive that under the, I'm sorry, the first step is we'll derive that under the null. So the null is what? The null hypothesis is that the sample average treatment effect is 0. So where would a sampling distribution of a sample average treatment effect with a mean 0 be located? Trick question, right? So SATE under H0 is going to be distributed normal with mean 0. And a standard error from the data. The standard error of the observed data. Then we'll compare that distribution to, I'm sorry, I'm mixing my metaphors here. What we'll do, we'll compute this probability distribution. This is some normal distribution, centered at 0, with a width determined by the standard error. Then we're going to look at what we did observe. We're going to look at the value we estimated from the data. So what's our actual value of X bar? We'll say X bar was here. And we're going to ask, if this were true, under this curve, what's the probability that we would observe a value of X bar? So, sounds kind of tricky, but it's actually quite straightforward. So, if I observed, if the null hypothesis were true, meaning the sample average treatment effect were centered on 0, what's the probability that I would observe something slightly higher than 0? Relatively high. What's the probability that I would observe something very far away from 0? Very low, right? That is our p-value. That's our significance test. How likely are we to observe what we did observe if this were true? Yeah, the graphic is what I want to go for. But so for our experiment, right, for our class size experiment, the null hypothesis is that the mean for the small class size minus the mean for the regular class size is equal to 0. That's the null, right? And then X bar would have a sampling distribution around 0 if mu were equal to 0, or if the SATE, the true SATE was 0. Under the alternative hypothesis, hypothesis 1, the difference in means is not equal to 0. So we're going to use an alpha 0.05, that's conventional. We're going to estimate the probability that we could observe the data, observe what we did observe, under the assumption of the null hypothesis. Assume the null hypothesis, assume no relationship, assume no difference in groups. How likely would we be to observe what we actually did observe under this hypothetical probability distribution? And we're going to use the normal cumulative distribution for this, right? The p-norm function. So how much probability mass is there at this value? Okay, so if our test statistic falls in this range, that is, it is more extreme than if it falls outside of the 95% interval that we've computed under the null hypothesis, if it falls outside of the middle 95% mass of the normal, we reject the null hypothesis. If it falls here or here, falls anywhere in these ranges, we say that this is probably not the distribution of the true sample average treatment effect. This is probably not the right sampling distribution. There's only a 5% chance that we would observe something so extreme. Right? And we say, you know what, I'll go with 5%. Now, on default, how wrong am I going to be? How many times out of 100 am I going to be wrong with this guess? With rejecting the null? How many times am I going to reject the null and the null will be true? 1 time out of 20, 5 times out of 100, 95%, right? So I'm baking in an error rate of 5%, right? Because this distribution, if value were here, it still could have come from this distribution, right? But it's unlikely to have come from it. If it's here, still could have come from this distribution. It's just unlikely. So 5% of the time, when I reject this distribution as driving the data, as driving what I observed, I will be guessing wrong, just by default. In reality, it's actually closer to like 40 or 50% of the time that significance tests are wrong because researchers make choices, but that's another thing altogether. But we have an error rate of 5% guaranteed, minimum error rate of 5% for this kind of work, right? So we expect by default 1 in 20 scientific studies at the 0.05 significance level to be wrong, right? Okay, so we'll reject the null hypothesis if the test statistic falls here, because we say it's highly unlikely that it would have come from this distribution. Now, if we want to up our uncertainty level, what do? We just shrink these intervals. We expand, we make this red area smaller, right? And we can make it smaller and smaller and smaller and smaller if we want to increase our certainty in the results, reduce our uncertainty that we've made an error in rejecting the null. So the normal CDF is symmetric, meaning we only have to go from one side to compute the probability that it falls within the rejection zone. What we can do is we can do 2 times p norm minus the absolute value of the sample average treatment effect from our normal CDF, right? So normal 0 with a standard error from the data. Don't worry too much about this, but we get a 0.187. So what does that 0.187 tell us? We reject the null hypothesis if p is less than the alpha value that we set, 0.05. If it's less than or equal to 0.05, we reject it. We reject the null hypothesis. So can we reject the null hypothesis here? No. Our model, so this model of where the sample average treatment effect could come from under the null hypothesis says there's a 19% chance of observing something as extreme as what we observed in the data under the null hypothesis model. So it's actually pretty common. 1 out of 5 times, you're going to see something as extreme as 3.5, which is what we observed under the null hypothesis. Pretty good chance, right? Pretty good chance you could observe this if the null hypothesis were true. So we cannot reject the null hypothesis under a 95%, a 0.05 alpha. That is, if we want to have 95% certainty in our results under replication, right? We can't reject the null. Meaning we have no certainty that there's a difference between the treated group and the control group based on the results of this study. We never confirm the alternative hypothesis. In this framework, all we do is reject the null hypothesis. Right? That's what we do when we do these significance tests. We just say, I have X amount of certainty that the result is non-zero, that the average of the sampling distribution of this statistic is not 0. That's what we're saying. So of course, we can do this more simply using the t-test function. Right, we can just do a t-test of the grade 4 reading for small and regular, and we can get a similar result, p-value 0.187 here. That's very similar to the z-test score we came up with here. Right, you'll see a very small difference between the t-test and the z-test. It's like a 0.002 difference here. But again, we get this 0.18 p-value, which tells us, no, we can't reject the null. There's no differences between groups here. And here's our 95% confidence interval on a t distribution rather than a z distribution, which is really similar to the interval that we estimated before. Right, before we estimated what, minus 1.7 to 8.7, and our t-test is estimating minus 1.7 to 8.7. So our Z and T tests come out really similar, and they will when n gets large. The only time we'll see a difference in a T test and a Z test is when n is really small. So for most real world work we're going to do, it's all going to be equivalent to a Z test anyway, because you're never going to work with data sets that are, 10 observations or so. We don't see that very often. Okay. So we're gonna see what time we got. We're getting close to time. Okay, so I've already harped on this, but these are difficult to interpret and they're often misinterpreted. So, as we start venturing into these, just remember your caution. These are tools that get misused often, right? And so I want you to kind of, as you start, going through this, just kind of keep that in the back of your head. All models are wrong, some are useful, right? This is a very useful thing to do, but it does not detect the truth, right? This is not a truth detection engine. This is a compared to a hypothetical engine under theoretical replication engine, right? There's a lot of assumptions that go into this. If we repeat the experiment many times and compare this to a hypothetical null, what do we see? That's what we're asking. Hypothesis testing is a deeply problematic feature of modern social science, right? This is uncontroversial, but I want to reiterate it. It's very problematic. So, for example, if we test 10 hypotheses in an analysis, which often happens, right? Let's say I have a study where I have 10 hypothesis tests baked in as part of my study. Just the likelihood that at least one of those hypotheses will be a false positive, meaning I'll reject the null when I should not have, is 40%, right? Because I'm doing 10, 95% Bernoulli draws, right? So I've got a 40% chance of making at least one erroneous conclusion if I do 10 hypothesis tests. That's troubling, right? And that's assuming that I've done everything else appropriately, which oftentimes is not the case. Okay, so homework is going to be using the Polls 08 data that we used in class today. There's a URL to read that in on the assignment, and I'll post it on Slack too. Do you all want to take 15 minutes to do a couple exercises together, or do you want to call it quits here?
That's why my train doesn't come for another
Okay.
30 minutes.
The exercise right after the compass photo.
Yeah.
And
Okay.
I'm immediately doing my homework, so I don't forget what it's for.
Fair enough. So we're going to use that criminal record data. Let me find it for you. Which homework was that? Maybe 4? No, I think it was 5. No.
3.
Keep going. Yes. Okay. Oh, right. And let me just, I just want to make sure you can pull the data up really easily. So yeah, it's the criminal record data. If you can find it on your computer, great. If not, I'm going to post it in the chat or in Slack. Okay, so you could just do read.csv on that. That's fine. That's fine.
So I got battery and I didn't bring my adapter for
No problem. Okay, so let's work through that real quick. Okay, so this is the data, criminal record data. Are you get it in? Okay. So we've used this before, right? But here we're interested in, actually, why am I like, let's work this out together rather than including my code doing it all for us. Well, yeah, maybe just, I mean, use them for reference, but we're going to work it out together too. Just think of it, it already has the solutions in there. Okay. So let's compute the sample average callback rate for black and white testers. How do you think we would do that? So we have read the data inappropriately. For some reason, I need to use read.csv for that. That's fine. Okay. So how would I compute the SATE or the sample average callback rate for black and white testers separately? So I could filter into different groups. That's typically how people have been doing it on the homework. Filter's fine. Or I like to do group by. Group by black is my variable for race, and then summarize callback what equals mean of callback, right? And that'll give me the proportion for each group that got a callback. So that's the sample average callback rate right away. What about for those assigned to the treatment? Those assigned to criminal record treatment, right? That's the focal question. So I can take that same code and modify one thing to do this. What do you think? There's one argument I can change to get black and white testers by criminal record. Oh, wait, I just want 4 criminal record treatments. Group by CrimRec, right? Categorical variable that takes on 1 or 0, treatment or control. There we go. Right now, if I want to look at criminal records for black and white testers separately, what do you think I can do? Think about combining the first 2 code chunks. How would I do that? So I could do 2 group by commands, or I could just do a comma. Group by CrimRec and black to get this table, right? And so this gives me row 1, no criminal record, white tester, 34% callback. No criminal record, black tester, 14% callback. Criminal record, black tester, 17% callback. Or white tester, criminal record, black tester, 5% callback. That's homework 1 in a nutshell, right? And then we could difference those off to get the estimated sample average treatment effect. Now let's compute the standard error for each group. So how are we going to start with that? Same thing we did before with the mean. It's going to be a summarize command. Summarize, the first thing we're going to do, that's right, is compute the SD equals the SD of callback. Right? How variable are the outcomes for black and white testers? Yeah.
So you don't have to be divided by that.
We're going to do that to get the standard error. Yeah. That's the standard deviation of
Okay, but
the outcome itself, but we want the standard error of the sample mean,
okay.
right? So we're going to
The
compute.
reason why we did divide by n for the like the Obama.
It's because those were already sample means.
Okay.
We had to take it, if we had them from voters, then it's because those were already, we were thinking about the sample mean of a average vote share, but we had to treat the process of interest as the Bernoulli voter outcome, right? What's the likelihood of each voter? And so the sum of binomials there was already a kind of aggregated variable, but we don't have that here. It was a repeated study, right? In effect. sorry, that was maybe not the best example to start with because it is kind of a step further. But okay, so we'll compute n is equal to n, right? And remember that that n function just counts the rows, which is useful. So then the SE is equal to SD over root of n. There's our standard error. So we have our standard deviation, our standard error. And notice and summarize, I can define SD here, define n here, and then in my third argument, I'm using those two variables I just defined. Right? Now I could combine this all into one line of code, right? I could just say SE equals SD callback over square root of n, but you know, sometimes being more verbose is good too. Okay, now again, just like we did before, how would I do this for criminal records? So that was for black and white respondents separately. What do I change to make this criminal records for standard errors across the criminal record group and the non-criminal record group? Just change the grouping variable. Right? And then for black and white testers, just add the race grouping variable. There we are. So I've got a lot of information here. This is great. Now, yeah, I've seen a lot of people on the homeworks doing like creating new data frames for each subset, using filters, and that's fine, but that could take like 30 lines of code versus we could do this in like 4 or 5 lines of code with a group by summarize. It's just a much more efficient way to handle it that makes it easier to read. And I think ultimately is, while it might feel more complex at the beginning, I think it ultimately is a far simpler way to approach the problem because there's less opportunity to make mistakes. Okay, so let's compute critical values for confidence intervals in each group. So how do we compute the, so at a 90% level, what's our alpha? At 90%, alpha is what? Is alpha is 1 minus critical level. Okay. So it's 0.1. And so to obtain our critical value, what do we need for the distribution? We need our z-scores, right? So what function do I use to retrieve my z-scores? qnorm. I use the normal quantile. Use the z distribution, which is just normal 0, 1, and qnorm function. So we'll call it crits. We'll call it z crit is qnorm, and then we do the p value we're interested in here, which is, so we have alpha is 0.1. Why? Alpha over 2, right? So we're going to take alpha over 2, 0, 1. And we'll get minus 1.64. And maybe we want to make, let's go ahead and get both of them just to make the vector operation a little easier. Well, okay, we'll set z crit and we'll add the plus or minus later. So at this point, we would either want to make it a vector with minus 1.6 and plus 1.6. So when we multiply it later, we'll get 2 values returned, which is what we want, or we could do it manually. Doesn't really matter. So then we could do, for each group, what do we need to compute the critical value now? The mean and the standard error. There you go. So let's get everything we need right here. Mean equals mean callback
right? That's all the information we'll need, right? So we'll call it CI data. So that's our CI data. So then we can compute from that. Let's do a mutate. And what are we going to do with our mutate? To create our 90% confidence interval. We want an upper and a lower, right? So how do we compute our lower? From subtract
Wait,
the z-score
times
times the standard error from the mean. So we'll say CI 90 lower equals mean minus, actually our z-crit is negative right now, right? So we'll do plus. We'll do plus or minus, right? It's negative here, so this is actually going to give us our minimum. It's a little confusing, but that's okay. We'll just call it CI 91 and CI 92, and then we can look at whether they're high or low after, right? So mean plus Z crit times SE. And then CI 92, mean minus Z crit times SE. That's it. So let's look at that. We get our confidence interval. Screen, of course. Spoke too soon. There we go. So our confidence interval, 90% confidence interval for the sample average treatment effect for white men with no criminal record, 0.276 to 0.404. 0.1 to 0.181 for black men with a criminal record, 0.116 to 0.217 for white men with a criminal record, 0.250 to 0.7 to 0.076 for black men with a criminal record. So looking at those CIs, what can you say? Does it look like there's differences across groups? So these two are the white groups, 0.276. Do these intervals overlap? They don't. That's pretty clear evidence that there's a difference between the criminal record group and the non-criminal record group for white men, right? What about for black men? They also don't overlap. But we could also compare the black group with no criminal record to the white group with no criminal record. Also a very clear difference. So across all four groups here, we see pretty clear differences. Our confidence intervals telling us that these are covering different regions of the probability distribution, right? And if we assume that those are accurate measures of the truth, right? That if we assume we've measured the sample average treatment effect for each group accurately relative to the truth, then it's pretty likely that we would see these differences even under resampling. Now, to change our to change it to a 95 level, if I've written my code like this, what do I have to do to change this to a 95% confidence level? Just change the alpha. That's it. Copy and paste is your best friend. And then now let's look at our CI data again. It should get wider, right? So we go from 0.276 and 0.404 to 0.264 and 0.416. Pretty straightforward. This is one reason why working in a kind of variable defined format is really nice, because then I can just switch out alpha to compute any confidence level I like. Yeah, rather than putting like 1.96 in there, like if I define z crit relative to alpha, and I define alpha as a variable, rather than putting in exact numbers, I can just switch out the variable. It also makes you less prone to error when you don't have exact numbers, because then you have to type those in over and over again, rather than just having it defined once. 99%, that's trivial, right? But let's see how wide that interval is now. Still, not that wide. Pretty clear differences across groups, even at the 99% level. Black and white testers, those 99% intervals do not touch each other, right? That's with no criminal record. With a criminal record, white and black respondents, we do see a little bit of overlap in the interval, right? These two intervals have a very slight overlap there, but that's because this is compressed towards 0. This is actually not a continuous space, right? Because it can't go lower than 0. And basically at 99%, we're saying 1% is the lower bound for black respondents, which is basically 0 in a context where our sample size is not massive. So it just can't go lower than 0. So we get a kind of weird, we can get compression effects on a 0 to 1 scale. Don't worry too much about that now. But okay, let's compute a significance test. Do we have time for that? Yeah, okay. So our significance test, where W indicates white testers and B indicates black testers. Our null hypothesis is what? How would I, so we're not going to compare criminal records, we're just going to do black and white testers at this point. Right? What does this hypothesis say? They have the same rates of callback, right? The null hypothesis is that there's no difference across groups. Okay, which is equivalent to saying the average for black testers minus the average for white testers is 0. So in R, we could actually just do this with the t-test function. So we could do this with t-test. What do we call this? Crimrat? We just call it DAT. You can just provide it with the two. I never use this function. You're never going to use it. So you know what we're going to do? We're going to do it as a regression instead. Let's do it as a regression instead, which is the same thing, which is what you'll actually do. So we'll call it model 0. It's going to be a linear model, right? Where our outcome is callback. Our predictor is black. Data equals stats. Okay, so now before what we did was we just looked at the coefficients of the model to interpret those, right? So here we're showing that black respondents have about a 16% lower chance of receiving a callback than white respondents here, right? Unconditional on anything else. So white respondents have about a 25% callback rate. Black respondents have about a 10% callback rate, right? Intercept here represents white respondents. And then to obtain the expected value for black, we just add 0.25 and minus 0.15. But if I do summary, I'm going to get a whole bunch of other stuff. And we're going to talk about this next time to talk about how to compute standard errors of regression parameters. But effectively, regression parameters are just sample means. They're conditional sample means, right? And so we get a standard error for our intercept of 0.02. That's our standard error for white callback rates in this context, right? And our standard error for black callback rates is 0.03, right? Here is our t-test. This is the probability that our estimate under the null hypothesis with this standard error is less than a critical value, or the probability that P is greater than T. In this case, 2 times 10 to the minus 16, right? That is 0, right? This is 2 times 10 to the minus 8. The stars indicate what threshold we're looking at. So 3 stars indicates this is statistically significant at a 0.001 alpha, right? So this says at a 0.001 alpha, we would reject the null hypothesis. This is the only way you're really going to be doing significance tests in R, is by using regression and by looking at regression coefficients. But here, we would very easily reject the null hypothesis. as we already kind of observed with our confidence intervals, right? They looked really different. Let's add in CRMREC and see what we do. And remember that for this data, the interaction model is actually what we're after. We don't want to look at Black and CRMREC independently. We want to look at them jointly, right? And here, right, we see that the model very clearly statistically significant, with the exception again of this Black times CRMREC, where the model can't say with certainty that Black testers with a criminal record have a different null distribution than white testers with a criminal record. But again, that's just because it's so close to 0, right? That's actually a function of the kind of model we've specified. This is a linear model, which assumes that, whatever, don't worry about that. But when you get to logistic regression, you'll see perhaps a better approach to how to model this kind of data. But very clearly, we can reject the null hypothesis, right? That there's no difference between criminal record and non-criminal record testers, and no difference between white and non-white testers. There are really clear differences across the board. Cool. So it's next time, we're going to talk about how to apply uncertainty to answering statistical questions in a way that's better than just saying yes or no, you passed a significance test. We're going to talk about generating prediction intervals for uncertainty. We're going to talk about inference in lots of different kinds of ways. So yeah, thank y'all for making the treks today. Stay safe in the snow. It's already gone. No, it's all gone.